Hello, welcome to episode, I think we're on episode 20? This must be episode 20. I'm going to say 20. Whew. Okay, so on episode 20, our goal is to start working on the keyword stuff. So keyword stuff is going to be a couple episodes in. So I kind of want to just work on it from this direction down, is what I think I want to do. So the thing with keywords is there's basically two different ways I could look at there's two different ways I can approach the problem. And I have a good idea of what both sides of this what two of the endpoints of the system need to look like. And picking one to start with is the first task. And I'm thinking I'd pick this one, but I'll explain what the other one is to you and talk it through real quick to make sure I'm making the right choice. So this side is all about encoding what it's going to be like to print out the code that correctly stores the token kind once we get it back from a runtime lookup that we have to write how it works, right? So right here we need to do some kind of runtime lookup. Now I don't know exactly what the runtime lookup needs to look like. That's one thing I don't actually know. But that's a detail I can fill in at the end pretty easily, right? I can adjust that to whatever the back side does. But what I do need to know here is sort of what does the information I have coming in look like? On the back end, I know how to sort a table, but I don't necessarily know. I know how to set up the hash table. What I don't know is what the incoming parameters are going to look like exactly, like what exact way I'm going to have to look things up. So I think if I start here, I can figure out what is the lexeme string that I have available to me. How is it formatted? Like how can I best? Well, what can I do with it? What's its starting point? And then I can switch back to the back end, write out the whole thing that does the hash table stuff, and then finally switch back to this and fill in the details about how to look something up in the hash table when it's done, right? And I also will know even if I don't know exactly what the hash table lookup looks like in terms of exact type information for it, I know exactly what I need it to come up with eventually. I know exactly what its final result needs to be in terms of its type. So once I have the final result, I know where to put that in the system and how to finish everything. So I think that's what we do. Now, there's a couple of things here we need to get right. So first of all, we have this fill token base kind. That relies on knowing the name at compile time, or rather at the generator's runtime, which we're not going to have in this case. We don't know the lexeme of the token. But our table can actually answer the same question that was answered before. So we're going to kind of end up with something that looks like this out the other side. We're going to have something that goes token.subkind equals, and it's just going to be a code right here, so it'll be like subkind and kind equals kind, right? So we're literally just going to have to get those kind and subkind variables as sort of direct results, but they're kind of both going to come back in a struct together. So this will be like lookup table, or I'll call this like keyword result, something like that. Now the other trick is that's not necessarily always going to have a result. So if I look over here at what my keywords handler is like, it has a keyword set. A keyword set can have a fallback token. And so what we want to do is say we have the idea that when we do the lookup, we don't necessarily find anything. And then if we don't find anything and there is no fallback, then this whole loop will have to continue and we'll go to the next handler. If we look up something and we don't find it but there's a fallback, then we'll do the same thing this does. We'll use the fallback directly and then exit the loop. When we use the fallback directly, we will have the fallback name, and then we can do basically exactly what this is doing, right? So we're going to kind of need a way to check if our keyword result has a result in it or not, first of all. Something like this, right? So if it finds a match, this is what you do. And if it doesn't find a match, then what? Well, then we need to talk about whether or not it has a fallback. So if the handler keywords has a fallback token, then what happens is same thing that happens here. And really we only do this else in that case, right? So if it has a fallback token kind, we go ahead and say there's an else case, and in that else case we grab, so it's not the handler token name anymore, it's now the handler keywords fallback name, right? So I probably want to just pull that out up here and just be like base name and stick that in there because that's a pretty long name and I'm going to have to use it again. Token name again becomes base name, and then the cool part is that structure actually could be used like this here, so handler token name, and then these are actually exact duplicates of each other like that. And so now it kind of seems like that wants to be its own helper probably. So a direct emit, will have the following things and going for it. It's going to have a scratch arena, a base name, and it's going to need the token set, and then it's going to need the output stream, right? And then we can just gen emit direct. Scratch tokens, base name, we no longer need that in a separate variable out. And here, same thing, except instead of base name, it's going to be this, which is probably going to want its own line. There we go. Now the keep looping has to be outside of the function call because we don't have the ability to alter that in a clean way from inside the function call, since it's local to this scope right here that we're already in, so that'll have to stay here. But yeah, that's neat. So now we can directly emit here and here and make sure that they're directly emitting in the exact same way. And that's all a fallback is that if we don't find anything in the table lookup and we have a fallback, we just do a direct emit from there. Cool. So the final question is, how do we get this keyword result at all? Because right now everything we have will tokens name. Oh, what's the matter? Oh, I have a token kind node. Token kind set. There we go. So everything here should just run just fine, right? Like we actually do get what we are expecting, but there is no keyword result here. So this code, even though it's generating without a crash or anything, won't compile when we try to actually run, like, you run this through the compiler. It's because this keyword result, it doesn't exist. I mean, there are other reasons why it won't compile. We haven't generated our token kinds or anything. But right now, the thing I'm concerned about is that we haven't actually told it how to find a keyword result. So there's another problem after that we're going to have to talk about, which is we also don't know, when we do find a match, how to prevent the next handler from triggering still. Does that make sense? Essentially, there's a chain of these handlers, and you can see right here an exact example. This is something I was worried about, but I wasn't sure how I was going to handle it yet. So we can see here we're doing a keyword check. First, we're doing a flag check. If that flag check is set, we do a particular find, and if we find something in this keyword lookup, then we want to not run this keyword lookup. Does that make sense? This keyword lookup has a fallback too, so even if this keyword lookup did fail, its fallback would trigger. We want to prevent all of that. So we need to, I'm noticing these little spots where I didn't put in new lines, which makes it a little harder to read for me. We want to think about how the control flow here should work. What's really happening is, if we do find a match, we kind of want to have one of those things where we can break out of a series of attempts, right? So really what's happening is everything inside this loop needs to be inside of one of those little do blocks that we can break out of. And again, the reason I use a do block instead of like a goto for this particular case is because I don't want to have to go through the work of figuring out a unique label for every time where this happens, because this is spread out in a somewhat it's not obvious that I could easily find every place where this happens and give it a unique name without doing some actual work. And instead of doing actual work, I can let the C compiler turn all of the break statements into a label that jumps to here by just using this trick, right? So now when I have a break, it is locally scoped to this do while, and I don't have to make a different goto label. Like, I don't need to make a different label that goes here and a different goto value that links to that goto label here. I can just use this generic system that doesn't need to change on a per keyword emit basis, right? Or rather on a per handler basis almost. At least on a per emit basis. I think that's what it would be. But anyway, we don't need it. That's the whole point. And so the way now is that when we find a match here, we break. Because of that, we don't actually need this else stuff. We just need, if we have a fallback, that we could right here put the fallback in directly. And so none of this is actually necessary. This is actually just literally doing what this is doing from a different source string, if it's available. And then we do the keep looping equals false, because once we hit something that always decides to emit a token, we don't need to check any more handlers. Just like our transition system in this model, when we're doing emits, the handlers go in order precedence. So whichever handler catches whichever handler provides a token type first, that handler wins, and none of the other handlers matter. That's why when we find a direct like a direct token type handler, we simply just take whatever it says and go with it. And same thing here. Now, as I'm looking at this, I'm kind of realizing I don't actually need this feature, this fallback of a keyword set. I could just emit a second handler for every direct handler, like turn this into this followed by one of these with this as its token name, right? That would work just fine. And there's literally no difference in the generated code because based on the way things are set up. So why keep it? Well, one, I've already written it this way. Two, it lets the model declaration code be a little more concise. What I could do if it really annoyed me that I had this extra usage of the same code right here that I have up here is I could do a pre-processing step to the model, the high-level model rewrites that says all emits for keyword emit handlers only do this part, and their defaults get split off into direct handlers. So I can fix that if it really matters someday, but right now it feels like it doesn't matter at all. It's just a tiny little glitch in the fabric of the system that, you know, I can manage that situation there. If it gets out of hand, the fix for it's not that hard anyway, so what's the big deal, right? Okay. Yeah. So we want to see like a keyword result again. And so now we can see what we have is this do while loop that doesn't actually loop at all. And right here, if we find a match, so in other words, when we do this, next thing we're going to do is insert code here that actually computes a keyword result. If we get a keyword result and we found that match, we'll set the token kind and subkind and break. Skip past the handlers down here, so it won't try again to find a keyword result. It won't even bother to do that keyword lookup. It won't potentially change the result, and it won't finally do this one. And if this one triggers, that break will skip over this too, so whichever one goes first will win the day. At the end, there's always going to be one that wins no matter what and doesn't need to break, and then we're done, right? Finally, we'll have to figure out how to emit a token once this is all done. But right now, our next goal is we need to figure out how we actually get this keyword result thing, right? So this is kind of what we need to get back from a keyword table lookup. But what do we have that'll let us look for one of these? Well, we have a couple of options. We have the lexeme just sitting here, and we're going to need to use that. We're going to need to use everything from emit putter to putter. So these two here represent what we have, but we also already have the size computed, so I could just use emit putter and size, right? So those are my two options. Is I could use a range, like a pointer range with two different pointers, or I can use a base pointer and a size. I think I probably want to use the base pointer and size. That's how I usually do things. But the other question is, do I want to have a function call that I hand write that isn't part of the generated code, but it supports the generated code that does a table lookup on a table data structure? Or do I want to do I want to automatically fill in a table lookup right here, like do the hash in this code and so on? Upsides and downsides to each. If I hand write the table lookup code, then it'll be a little easier to write the table code. Writing code that gets generated, you have to put in the new lines yourself. You have to you lose indentation a little bit, so it gets a little harder. There's a number of things that are a little bit harder about the writing. If you don't have any, obviously this kind of code, right here, is a good example of code that doesn't actually have any dynamic features, right? This code comes out the same every time we reach the point where we want to generate it. We just generate that same thing. But there are plenty of times when generating code that, right up here, the code we put out right here is sort of algorithmic. It's determined by an input. So if I ever want to intermix them, I want to be in the situation where I'm doing generated code, not handwritten code, because inside of handwritten code, inserting generated code is much harder than it is to insert what is essentially handwritten level code, but actually by just generating it, right? Generating handwritten code like this, easy. Inserting generated code into handwritten code, not so easy. So if I want any part of my table lookup stuff to be generated, I need the whole thing to be generated, essentially. Or at least I need to figure out how to isolate the generated and non-generated parts in a way that will be more tricky anyway. So I need to think through what options I have there. I want to generate the table itself, for sure. But that's just a data structure. That could be separate from the lookup algorithm. However, when I go to generate the table itself, I might want to alter the hash function in order to if I'm allowed to alter the hash function, I might be able to find a proper hash, a better hash function for a given set. So given any particular set, some hash functions will just happen to have less collisions than others. And it might be possible to try 20 different hash functions and pick one based on which one works best at a particular size. And if none of them meet a particular threshold of minimum collisions, then we increase the size of the table and try them all again, right? The point being, we want to find, since we get a chance to do something we don't usually get to do with hash tables, at least when I write hash tables, they're usually dynamic. The things that are getting inserted to them are discovered over time at runtime, and so you don't really have any way of thinking about improved hash functions. In this situation, we know exactly what set. The set we're trying to represent is static, so it can't be grown, it can't be shrunk, nothing can change about it. It is what it is forever, and that means we could let the optimization time of the generator run, do a little bit of work to pick a good table layout. Hopefully what I'm saying makes some sense. If I want that freedom to change the hash function, then at least part of the table lookup has to be generated, right? Well, not necessarily. The table lookup could still use a hash function that is handwritten if it uses variables, if my hash function can be described as just a variable, right? If I can just say, here's a pointer to the function that is the hash function, or better yet, here's a 64-bit integer that is a parameter into a hash function, and the way I generate a hash function or pick a hash function is I just try different random 64-bit values, and I try 100 of them, and I find out if any of them work particularly well for this set, and if not, then I'm just whatever, I didn't find a good one, grow the table, try again. And in this process, I'm just looking for the best 64-bit number to use as sort of the I don't know what you call it, the seed of the hash function or something like that. It'd be the fixed parameter. And then I could write one hash function, but handwrite it, but pass in that 64-bit value to each of them as a parameter. And which value I pass in is based on which table I'm generating from. So then I wouldn't actually have to generate any of the lookup code. I could handwrite the lookup code, but I would generate along with side the table a number that gets used during the lookup. So it would just be an extension of the hash table format. The only disadvantage to that is that anytime you can put a constant in your code instead of a variable, you have the potential, not the guarantee, but the potential for that to maybe be less work. Like you don't have to, if you have to pass something as a function, like a function parameter, that takes up more space on the set of registers that you're passing around. You have to do the read from a variable somewhere not like co-located with the code necessarily. Although if it's a 64-bit value, you probably would have to do that anyway. I don't know. Maybe not. Maybe it would be able to build it in. I really don't know. I should know more about how that part of x64 works, the constant numbers actually, to make that determination. So since I don't know either way, and the easier thing to do is to hand write the lookup code and to generate a parameter that is specialized for that table, that's what I'm going to do. When we're going to generate the table, we're going to try different hash functions by altering a 64-bit code that is simply a parameter to the hash function, and finding one that gives us a good shuffle of the strings so that we get as few collisions as possible, while also trying to minimize the size of the table itself. Once we have that table generated, we can handwrite the lookup code for it, and then put a call to that lookup code right here, and that's how we're going to proceed. So let's switch to that side of the problem, because I know exactly what that part needs to look like too. We know what the sort of resulting type of the system needs to be, and we know what the generator for the table needs to look like. The thing in the middle is going to be the handwritten part that just glues those two things together, and that'll come last. So let's switch over to that. Where I want to put that is kind of an undecided question. I think we kind of want that to be like its own concept, because not all, but very many of the ways I might go about writing this system want this same exact hash table optimization at some point in their control, like in their system, right? So give us an outstream, give us, let's see, I'm gonna need keyword set. Here's the keyword set I want you to generate off for. Yeah, the fallback name has literally nothing to do with anything right now. Yeah. Then I want I'm going to need the token kind set as well, so that I can turn token names into base types, because that has to get stored into the table, into like the values of the table. Okay, and I'm probably going to want to scratch. Just guessing, but probably. Okay, so that's going to be my gen keyword table thing, and the trick with that is going to be that needs to get called here inside of a loop that I don't even have yet. Over all of the keyword tables. Now the next question is keyword set. Do I actually have... I don't have a list of the keyword sets. So what I have to do to actually do this is I have to see which keyword sets are actually being used by emit handlers. So to do this properly is going to involve looping over all of the states, all of the transitions in all of the states, all of the emit handlers in all of the action lists of all of the transitions of all of the states, in each of the emit handlers, checking to see, okay, let me start over, because it's a little bit different from that. It's looping over all of the states, looping over all of the transitions in each state, looping over all of the actions in each transition, for each transition, checking to see if there is an emit rule in any of its actions. For each emit rule that we find, we have to loop over its emit handlers and see if it has a keyword emit, like a keywords emit kind handler, right? See if there's an emit handler of the keywords kind. And once we find that, we have a keyword table, and then we need to check if we've generated that keyword table already, and if not, then we generate it. Sounds kind of ridiculous, right? I don't like that plan. So what I'm going to do instead is we're going to extend the idea of the Lexer primary context to have keyword set list. And that's just going to live right there. Our keyword set up here is going to first, last, count, next, and now whenever I create a keyword set, I want to give it a pretty name. So these will be main keys. These will be PP directives. These will be PP keys. So that's keyword set. And then I need this to have a pretty name. And I need to go to the spot where I create keyword sets down here. This is going to take a pretty name, and it's going to have a wrapper that takes the same parameter as a pointer and does the conversion. And keyword set, named putter, Lexing to putter. Push string copy, helper context arena, pretty name, and then what we need to do is take the primary context and push this onto its list. So primary context, I'm sure I have other examples of this type of thing somewhere, but even if not, let's just pound it out the way it is. So I want the helper context primary context dot keywords first, last, here's the new set, and then you can take the keywords count and increment it by 1. Okay, so that's pretty cool. Now all we have to do down here is a loop, a singular loop. Now there is a question of, shouldn't I be optimizing out these keyword tables? The answer is yes, I should if I really wanted to do a good job. But the good news is these are only going to take up, these are only going to be extra data. So any keyword table that exists that isn't used ever is just, all it takes to eliminate it is to not declare it in your model. So I'm not too worried about that yet. Certainly at some point I should optimize this out, no question. It's just low, that's like low priority at the moment. I wouldn't feel too bad if I ended up having to ship this code without that in there yet. Keyword set, I'm going to call this set equals context keywords first. Node means set, keywords means star set, and gen keyword table. Whoops, you can go away. Alright, everything builds. So the next question is, can we implement gen keyword table? So, a couple things we got to do. One, we need to we already have a hash table, right? But what we actually have to do here is build our own hash table, kind of, because that hash table there is going to use a fixed layout function, and we kind of want to see what the layout would look like under different functions, if we're going to do anything fancy at least. So we can't rely on that. Plus that thing, like, it's just, it doesn't, it's, we can, it's, that's based on trying to make it easy to be type generic in C by just doing bit matching and stuff. We can do a little bit smarter work than that in this one, so that we don't have extra indirections or anything. I suppose the first step is just to figure out where each of the keys go, and then the second step is to figure out, like, is to make the parallel table of the result types, and those will not be that hard to make. That's actually the easy part. The interesting part is how to arrange the keys. So let's start by just making something that can lay out a single table and score it, right? So we'll call this like keyword layout, and I'll ask for it to, I guess this is an optimization, opt key layout. Here are the keywords of interest. Here's the scratch arena on which I want you to put the keywords, and here is the, I don't know, the 64-bit value that I want you to use as your seed, right? We're going to stick all of this inside of a scratch, because when we're done, none of what we did will need to be leaked out. Nobody else needs that memory, and so there's no point in keeping it around. So temporary memory block for that, and then then the next thing we would need to be able to do is, once we picked a key layout that we liked, we would want to be able to generate the tables off of that. But I think that step one is get the key layout correct, and the generating part is not the hard part, right? That's kind of the fun, easy part. So let's work on key layout for now. That's an optimization, but I'm going to stick, I always stick my structs all in the same place, so I'm going to call this a keyword layout. Don't know what type it needs to, like how that type needs to be structured yet, and it's going to live up here in this region. Now, what parameters did I say key layout would have? Arena, keywords, and a seed. That makes sense. Okay, so then what this needs to do is it needs to have a score, and the score is going to be such that 0 is the best possible score, and anything larger than that is, you know, so this is more like error total or something like that. Error score, something like this. And the rest of it, I believe what it needs to be is simply assigning, I guess what we should do is we should say, in addition to this, we want to say slot count, right? So there's like, how many slots do we want? And maybe we'll start with keywords.count slots, right? So exactly one key slot for each keyword. And then what we want is, over here, we're just going to have something like maybe for each slot, the node that goes, the keyword node essentially that got paired into that slot. I think that would be enough information, and the ideal type for that information. So slots, something like this, and then the process looks like this. So we create a layout, and we say that the layout.slots equals, and we just push that right onto the arena right off the bat, keyword pointer slot count, right? So there we go, and we want those to initially all be zeros. Now what we're going to do is basically write a loop that visits every keyword in the set and adds it to the hash table, and then returns the hash table, and that's it, right? And what we're essentially doing is, instead of actually creating a hash table that we mean to look things up with, we're creating the hash table for the purpose of generating the table, like generating an inline table, like a C declaration of the data, essentially, right into a C source file, right? So we don't really need to optimize this for being something we can do lookups on at all. We are actually just running this to see what would the layout be after this many inserts happened, right? And the other cool thing is we don't have to like do anything complicated to figure out what to insert. We actually already know what we're trying to insert. That's in the list. The only thing we're interested in is how those things end up getting laid out when we do all of the inserts, as I've already pointed out once. So let's do the loop, see what we get. Keyword equals keywords first. Okay. So we're visiting each keyword, and what we want to do is we want to make the lookup key be the lexeme. We're trying to go from lexeme, as we're trying to like the calling codes to this, the thing that is looking stuff up in this table will have a lexeme. So it's looking for this as its value and this as its key. And so we're going to look at this keyword and we're going to go, let's hash the string, the lexeme, right? So how do we do the hash? Well, that part we're going to need to take a moment for. So I think what we actually want to do is we want to say that there's a function that is a part of this system here, right? Or rather, since we're generating these here, at least it needs to live right here, like in this file or something, right? But that's not even quite right, but I think for now that's what it can be. Where exactly this needs to live is a little confusing. That'll have to be something that gets worked out over time, I guess. So all we need to know is that it's like the Lexer hash, right? Maybe lexeme hash. And then what we want is that lexeme hash takes a seed, and it takes a base pointer and a size, right? And what it does with that information is I don't know. Usually something like we do a loop, at each step of the loop we're going to take some way to combine a result with the pointer we have so far, and also with the information we already have. So like it wants to be like result plus equals that, but we want the result that we previously had to like get shifted up by a few bytes or something. So it's like plus result shifted up by 6 bits, so that for the most part it won't be a problem. Maybe XOR those together, right? And then the question is, how do we involve the seed in all of this? And maybe the answer is we involve the seed. So there's a couple things I want to watch out for. If I just did this, then the first byte would eventually become irrelevant, right? See what I mean? The first byte that goes in here would get lost after enough shifts had pulled it all the way off. So this maybe is not a good idea, unless I include something like this in there as well, you know. So like this, maybe I'm at each stage I'm taking what I already have and I'm XORing it with the next byte, and the same thing I already have shifted up 6 times by 6 bits, right? And then the other thing I want to do is probably multiply that by the seed number. If the seed is 0, that'll cause some weirdness, so maybe not. Maybe what I want to do is take all of this and just say that it's plus the seed. What effect will that have? That'll say just take the thing you would have done and rotate it some before you XOR it in. I think that's not a bad idea. I don't know. That seems good to me. That seems good to me. So that'll be how we can just sort of stick in different seeds and see if by sticking in different seeds we can change the error at all, which will be neat, hopefully. If not, maybe there's a better way to do that. I'll have to, you know, hear from someone who knows more about hashing than me, but I think something like that is a fine starting point. Usually someone would say something like stick a prime number in there somewhere. Felt like I had a sneeze coming on. I don't think anything's like jumping out at me now that is wrong with that setup. I guess the only obvious thing is that I'm not incrementing my putter at all. Yeah, I'm happy with this. Okay, so I guess the way I could stick in a prime number is by saying instead of bit shifting this, let's say 2 to the 6 is what, 64? So a nearby prime number to 64 is 59. Wait, is that prime? Or is that divisible by 7? 50 to 49. No, that's not divisible. Okay, that one's prime. One of those, there's one in there that sneaks up on you. I want to make sure 59 is not prime. Is prime before I say that. Is 59 prime? Yeah, 59 is prime. I think it's 51 is the one that will get you, or maybe 57. Yeah, 57 I think is the famous one that looks very prime and isn't, not 59. Okay, good. Alright, so that's going to be the hash function. Okay, mostly pulled that out of my butt. But, moving on. So, we put in our seed here. We take the keyword name string and the keyword name size, and like that we now have a hash. Okay, so I take my hash and I want to say stick this into one of these slots here. So what I need to do is figure out first index. First index will be found by taking the hash modulo the slot count, and now I'm going to take an index, which is my first index, and I'm going to just start looking at each spot in this in these slots array. So if layout.slots I is equal to 0, then I can insert here and then break. Otherwise, I need to increment I by 1. If I comes to the point where it needs to wrap over, then I equals 0. If I, and by I mean index, my bad, is equal to my first index ever at this point, it's time to break. Index, 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 right? So the first time through I'm at my first index, I check it out. If I move past it, and then later I end up at a point where I increment into the first index again, then I've done the whole loop and I can break. This is actually more like invalid path in this case. So I guess kind of the rule is like if slot count is less than keywords count, then maybe what we do is we just bump it up. Or rather, what I mean to say is slot count equals clamp bottom slot count keywords count, right? Okay. So we do the insert. I should probably stick a slot count right here. Just feels wrong to not have it, since I'm modifying it off of that input slot count now. And so if we find a spot where we can do the insert, then all we need to do now is store the keyword pointer right there, I think. Right? So we're taking these pointers and we're storing them into these slots here by basically doing a hash and then doing a linear probe to find the spot. Now, there's all kinds of stuff we could do to be fancy. We could say we don't want to do linear probing, we want to do like, you know, exponential or quadratic or whatever it's called, probing, or other fancy systems of looking up. Like if we did a Robin Hood hash here, for instance, would make a lot of sense because the Robin Hood part is where you shift things around is a little bit complicated and expensive, but we could get that all done at compile time, and then at runtime you would just run a normal linear probe, but you would have minimized the average cost, or rather like you would have minimized the, if I remember correctly, the way it works is you minimize the cost by doing that, or rather you shrink the cost, not necessarily minimize. I'm trying to, let me think that through. I'm pretty sure you end up in a situation where the cost is actually the same, but it's like more evenly distributed, which would be nice to have. If we did something like, you know, there's so many ways to hash. If we did like a cuckoo hash thing, then the lookup would just involve trying those two different hash functions, right? We'd basically say there are two hash functions, and you try both of them, and you find your result that you're looking for at one of those two spots always. So it doesn't really matter which order you do them in, but you do one, then you do the other, and one of those two will have your result always guaranteed. And so then what the optimization has to do is try to make it so that it can find the smallest table that allows it to lay everything out that way, and then pick while also having to pick what those two functions are. It's a much more of a it's a space where you could do a lot of optimization work to get a really cheap lookup. So there's a lot of options there. Something I never get a chance to play with, so I don't actually know where I want to go with it. But I think I'll just stick with what I know in terms of basics for now. So we're going to lay this out with basic linear probing. Yeah. When we're done, all I want to do is I want to keep track of the total cost. So the total cost, or error score here, goes up by 1 every time I have to do this. Now, I'm kind of saying that I'm always going to find a place to lay something out, so it's not even valid. Like, there's no such thing as a situation where this gets incremented incorrectly, right? Every time this happens, it indicates that the first index, or that the spot where we landed was past the first index. But we're always landing somewhere, or else we're hitting this invalid path thing anyway, right? And when this is done, what we'll have is an error score, which tells us how many extra steps have to be done if you want to look up every keyword once. There might be an argument to be made that we want a few other error criteria, like the Robin Hood system decreases the maximum error for any particular slot. You know, maybe we want to look at that too. Maybe that means something at some level, but I think for now I'm just going to keep things simple and say we're going to try to minimize total error across the table, where error is how many extra steps of probing you have to do off of your initial guess to find a slot that's available. so that when it's lookup time, that'll translate into how many string comparisons you had to do to find the thing you were looking for, right? The other thing I can kind of do with this is I could keep track of if every keyword has its own hash, because if every keyword does have its own hash, then I don't actually have to compare strings unless I see that their hashes match, and there's then essentially the only reason you're comparing strings is to determine if it's a keyword or an identifier, right? If all the keywords have different hashes, then if I find two hashes that match, I can compare the strings directly, and I don't have to compare ever again after that, because either those strings do match and this is the keyword, or they don't match and this is an identifier that just happened to have parsed to the same keyword, or hashed to the same hash, I should say, and either way it's not a keyword, right? Or either way it's not any of the other keywords on the table, I should say. And that would also save me having to do a bunch of string comparisons along the way. So there's probably a lot to be said for storing our keys as an array of hashes first, and then an array of strings second, and then finally having a separate data array as our third array in the table. Yeah. Yeah, okay. So there's the key layout code. For now, we're just going to try to see how that goes. So is everything building? What's going wrong here is I got a key layout, but I didn't use it. So I'm just going to start by I'm not even going to bother actually printing out code. I just want to see some metrics. So what was the error score of this? Question number 1. And I'd kind of be interested just to see if I can look at the table just for funsies, make sure it makes sense, you know. Keywords first. No, this is wrong. I want to look at slot count. Keyword equals key layout dot slots I if keyword equals 0 f printf standard out keyword lexeme. So here we go. I've got my list of keywords here. My total error score here is 230. Now that's not surprising because I have this is equal to the total what's the word I'm looking for? This is equal to the total number of keywords available. So I'm not giving it any spare room. There won't be a single null in here because I've made it lay out all 66 different spots with without a single extra space. So it's gonna have a hard time finding a seed that actually does that. But I'd kind of like to play with the idea of what if I change the seed? Does that change the error score? So that changed the error score dramatically. By 24, we can do stuff with that. If it can go up that much, can it go down that much? 462, 324. Say I put in something bigger. 312. There's it's gotten smaller. 226. 158. Yeah, so just changing that number a few times, you can get a lot of leverage, right? Like which number you pick there makes a big difference to how good that hash is. Now, obviously, the other thing you can do is just make this bigger, and that should help a lot. So that just dropped us down to 30. And let's say I'm in that range, I do a couple changes, and look, I'm still finding improvements by just making completely garbage changes, right, that mean nothing at all. I'm not basing this on guessing. I'm just doing a randomly generated. I'm not even doing randomly generated, but like a random generator, 18, right? So we can count on, if we did like 20 or 30 random numbers for the seeds, finding a good seed to minimize the total cost, and then if we combine that with slowly stepping this size up. So what if I don't go all the way to double? What if I'm at like a small fraction above? So 96. What if I do 20,000? Do I get better or worse? Worse. Okay, what if I do 20,001? What do I get? Better. You know? Yeah, this will work. This will be a good way to do this, I think. We'll be able to find pretty good tables. This isn't like a super hardcore solve or anything, but it's gonna do a pretty good job of finding somewhere good, I think. And then what we can do is, once we find something that's like within a particular threshold that we like, we can slow down and spend more time checking out hashes there, trying to shrink the table by 1 or 2 more slots, you know, let it like spend one pass. Just like early on, it'll just be looking for like a cap, like it says, okay, at this size and seed we hit our threshold. Can we remain within our error threshold while shrinking the table back down little bits at a time from here, right? And then it can try more seeds because it already is kind of like narrowed down the space a little bit, right? So this is going to work out pretty well. So that's how we'll do our layout, is we'll be able to manipulate this with a random number generator, and this by slowly stepping it up, looking for a layout that minimizes the error score. So that's what I want to do next. Is that opt key layout that I have there is sort of just the basic opt key layout. But what I really want, okay, first of all, I should separate this differently. I want this to live essentially in its own universe. So I'm not even going to put it below a single other function. Yeah. There we go. Its own universe. Okay, next up, when I do opt key layout, this we can do smarter now. So what we're going to do is we're going to do keyword layout, and we're going to do opt key layout, and we're going to pass in an arena, but we're not going to pass, and we're going to pass in the keyword set. But we're not going to pass in those 2 hints. This is going to be the one that's going to determine the slot count and the seed from like an iteration, and then it's going to return it out there. So that'll be our next goal, is to write a good version of opt key layout that works without us giving it the starting information, and instead explores the space of these 2 parameters to find the good starting information. Okay? Alright, so see everyone next time on that episode. That'll be fun. Bye-bye.